Delta rule. Delta rule. In its original form, the delta rule assumes that the activation function for the output unit was identified function. So this mathematical derivation is like that. Then a simple extension allows for the use of any differentiable activation function. We shall call this extended delta rule. So the first equation and the second equation is, here are some difference, so we should remember this. Now we will learn about hetero-associative memory. Associative memory. Neural networks are nets in which the weights are determined in such a way that the net can store a set of p-pattern associations. Each association is a pair of vectors SPTP with p12 p. Each vector SP is an n-tuple and each TP is an m-tuple. The weights may be found using Hebb rule and delta rule. So here we can get some idea about hetero-associative memory. Associative memory neural networks are nets in which the weights are determined in such a way that the net can store a set of p-patterns. What is p-patterns? P-patterns association is very important. Each association is a pair of vectors. Each association is a pair of vectors like SPTP with P's value can be 1, 2, 3, p, etc. Each vector SP is an n-tuple, means it has n components, and each TP is an m-tuple. Then the weights may be found using Hebb rule or delta rule. Here are figure for hetero-associative memory where x1 is connected to y1, y1, yj, ym, all types of y, and here is the weight we are seeing here. Similarly, xi, xn is connected to y, this kind of way. Here x1, xi, xn, etc. are input units and y1, yj, ym are output units. So here are some example of hetero-associative memory. Binary pattern pair S2 with S and 4 and T2. Total weighted inputs to output units Y. Associative function threshold is like this. Weights are computed by Hebbian rule. Sum of outer products of all training pairs like this. Training samples is like this. Example of hetero-associative memory. Here is we can see an example of hetero-associative memory. Here is ST1S and T1 is looking like this. By multiplying two matrix, we can get this matrix. Similarly, ST2, ST2, ST2 and T into 2 of T, we can get this type of matrix. So W is computing all weights, computing all weights, we can get W. Here by computing all weights we can get our W. In this example, we can see the recall. Here x is 1 0 0 0, x is 1 0 0 0, similar to S1 and S2. By multiplying weight and x, that means input and weights, we can get this output. So y1 will be 1 and y2 will be 0. By this we can get x as. Similarly, in this matrix we'll get y1 equal 1 and y2 equal 0. Similarly, this. Now we'll learn about auto-associative memory. For an auto-associative memory net, the training input and target output vectors are identical. I am repeating that for an auto-associative memory net, the training input and the target output vectors are identical. The process of training is often called storing the vectors, which may be binary or bipolar. The performance of the net is judged by its ability to reproduce stored patterns from noisy input. Performance is generally better for bipolar vectors than for binary vectors. Here, auto-associative memory is same as heteroassociative memory nets, except TP equal to SP. Used to a recall pattern by its noisy or incomplete pattern completed pattern recovery. A single pattern is like this. Here, weight matrix like this. From this we can get training pat, noisy pat, missing info, more noisy, etc. etc is more noisy, not recognized. Hey, Gandhi sir. Here still that's it. Auto-associative memory. The proceeding process of using the net can be written more succinctly as like this. Here, this matrix is multiplied by W and we get this, and now therefore as before the difference take one of two forms: mistakes in the data or missing data. The only one mistakes we consider are changes from +1 to minus or vice versa. We use the term missing data for refer to a component that has the value 0 rather than either +1 or -1. Iterative auto-associative memory. In some cases, net does not respond immediately to an input signal with a stored target pattern, but response may be enough like a stored pattern. Testing a recurrent auto-associative memory net stored vector with second, third and fourth component to 0. So it matrix to store a vector 1 1 1 minus 1 is like this. Bidirectional associative memory (BAM), first proposed by Bart Kosko. Bidirectional associative memory is first proposed by Bart Kosko. Heteroassociative memory. It is a heteroassociative network. It associates patterns from one set A to patterns from the another set B and vice versa. Generalized also pursued correct outputs despite corrupted or incomplete inputs. Consists of two fully interconnected layers of processing elements. There can also be a feedback link connecting each node of itself